Okay, everyone, what's up? Welcome back. Today we're going to get into a little bit more of section 3D. We're talking about isomorphisms and isomorphic vector spaces. So, last time, if you'll recall, we finished it out by talking a little bit about isomorphic vector spaces. So an isomorphism was an invertible linear map, and two vector spaces are isomorphic if there's an isomorphism from one to the other. We said, hey, let's prove something about this, and we found that two finite dimensional vector spaces over a field, the same field, are isomorphic if and only if they have the same dimension. So for finite dimensional vector spaces, dimension completely characterizes isomorphism. Cool. The proof of this was kind of long, but hopefully not too bad. Today, we're going to make do some applications of it. We're making use of this. So first off, let's show that LVW and FMN are isomorphic, where M and N are the corresponding dimensions of W and V. So here's the statement. Take V1 through Vn to be a basis of V. This here says the following. Dim V is equal to N. And let's take W1 through Wm to be a basis of W. Okay, that says, i.e. dim W equals M. Then the map that takes a linear map T and two bases and spits out a matrix, that is the matrix representation of a linear map with respect to a basis of the domain and the codomain, that map is an isomorphism between LVW, the linear maps from V to W, and FMN, i.e. the field, the field M, the matrices over the field with dim W rows and dim V columns. Okay, cool. Right on. That makes sense. Okay, let's prove it. So, if you'll recall, we have previously showed that this map M is linear. So, from a previous section, that is when we introduced this map M, we know that M is linear. Okay. So, to show M is an isomorphism, it is enough to show that M is injective and surjective. Okay, first off, let's do injectivity. For injectivity, suppose T is an element of LVW, and suppose that it is such that M of T is 0. Then, here's what this says. This implies that T VK is equal to 0 for K equals what? 1 all the way up through N. Why? Think about it for a second. The idea of it is that the matrix of a linear map tells you how to take the coefficients in one representation of a vector and send them to the coefficients in another representation of the image of that vector. So, if you'll recall, I'll write this up here briefly. The way that M is defined is as follows. So let's let A be the matrix of T with respect to these bases. Then, here's the idea. It's T of The whole gist of it is as follows. So T of VK is equal to the sum of AJK WJ for J equals 1 up to M. That is, the matrix A tells you how to rewrite the image of VK as a linear combination of the W's. Okay, so the image of a basis vector in V in terms of a linear combination of your basis in W. So this is what the entries of this matrix are. So if you get out the 0 matrix, then that says that no matter what basis vector you put through, you get out 0, the 0 vector. Oh, okay. There's only one map that does this. There's only one map that is 0 on every element of a basis. So since V1 through Vn is a basis for V, this says T is 0. Hence, null space of M is just 0. Oh, and M is injective. Nice. Okay. For surjectivity, the linear map lemma gives us what we need. The linear map lemma says that for any A in Fmn, there exists T in LVW such that the following holds. T of Vk is equal to, well, you guessed it, the sum from J equals 1 up to M of A, JK, WJ for K equal from 1 all the way up to N. Oh, remember what this says is that, hey, if you pick here's basically the idea. If you pick what every basis element should get mapped to, then you have a linear map. That is what the linear map lemma says. So all you have to do is decide what basis element should get mapped to, and then you get a linear map that does that. Okay, here's a particular way to do it. This particular way does it in such a way that pretty much by construction, A is the matrix of T. This is just MT. So M is surjective. Hence, it is an isomorphism. It's injective and surjective, and so it's an isomorphism. Very cool. All right, what's a consequence of this? Here's an easy one. Now we can finally tell the dimension of LVW. Oh, here we go. Okay. So if V and W are finite dimensional vector spaces, then the vector space of linear maps from V to W is also finite dimensional, and its dimension is equal to the dimension of V times the dimension of W. By the previous result, here's the proof. Not a lowercase l, a capital L, LVW, and F dim W dim V are isomorphic. But by the last result from last time, this means they have the same dimension. So the dimension of LVW is equal to the dimension of F dim W dim V, which we know the dimension of Fm comma n is m times n. So this is just dim W dim V, which is what we wanted to show. Sweet. All right. So we can do some stuff. As soon as we have an isomorphism, as soon as we're able to talk about the concept of vector spaces being the same, just maybe labeled a little bit differently, we now have the ability to answer questions by moving them to a context where it is easier to do so. So instead of having to try to find a basis for LVW and prove that this basis is the same whenever, or this basis always has the same length no matter what W and V you pick, provided that they are of the same dimensions as the other W's and V's you might pick, that is for fixed dimension. Instead, now we can just move it straight on over to F dim W dim V, and that one, we already know how to calculate its dimension quite easily. So this is a very good trick. Let's use it some more. Okay, so here's the next thing we can do with all of this. It's actually really nice. It's very easy. It will bring us back to something that we are familiar with. It is dealing with matrices and matrix multiplication and taking a vector and multiplying a matrix by that vector. Or taking a matrix and multiplying it by that vector. Yeah. So linear maps, let's turn it into matrix multiplication, return to a familiar context. The point of this is not to just go back to what we were doing before, but the point of this is to see that what we were doing in our first linear algebra class was just a particular way of looking at what we're doing here. If it is convenient sometimes to look at things in that way, we'll do so, but the generality of how we've built things out so far is nice because we aren't forced to look at things this way if we don't want to. Let's make it clear what I'm talking about by getting into it. So the first thing we're going to do is we're going to define the matrix of a vector. So let's suppose that V is a vector in a vector space and that V1 through Vn is a basis of V. That is, i.e., dim V is n. Okay. So the matrix of V with respect to this basis, it's an n by 1 matrix that looks like this. It's B1 through Bn, where B1 through Bn are scalars, such that V is a linear combination of V1 through Vn using the b's in this vector as the coefficients. Okay, cool. Not too crazy. You can write every vector as a linear combination of a basis, and you can take those coefficients and stack them up in a big rectangular array like that. So, does this work nicely? Yes. Okay, here's two results. The first one is so straightforward that I will not say it, or will not prove it. It says that, hey, suppose you've got T, a linear map from V to W. Suppose that V1 through Vn is a basis of V, and W1 through Wm is a basis of W. Then the kth column of the matrix of T with respect to these bases, which, if you remember, we just write the matrix, then a dot comma k. So the k part is in the column. The dot says range over the rows, fix the column. Okay. That thing equals the matrix of the vector tvk. Ah, okay, very cool. Think about this. The matrix of tvk, well, that is something that lives in W, right? So this is with respect to the basis W1 through Wm. Right? Okay. Well, what this is saying is that the linear combination of W1 through Wm that gives you tvk, its coefficients are precisely the kth column of the matrix of T. But that's exactly how the matrix of T is defined. The entries in the matrix of T are the coefficients that that you use to write the image of a basis vector in the domain in terms of a linear combination of the basis of the range. The coefficients are precisely the columns. Oh, so this is like just definitionally true. all I would do for a proof is just recall the definition of the matrix of T, recall the definition of the matrix of a vector from right here, and then just write them down, and you would notice that they're equal. So instead of me just rewriting definitions, if you don't believe it, go back and look at the definition of the matrix of T and convince yourself of it. So let's prove something that maybe is slightly less trivial, which says that the matrix of a vector and the matrix of a linear map work together quite nicely. That is, if you take a linear map from V to W and some vector V and V, okay, then for V1 through Vn a basis of V and W1 through Wm a basis of W, the matrix of TV with respect to the basis W1 through Wm, since this is a vector in W, is equal to the matrix of T with respect to these two bases times the matrix of V with respect to this basis V1 through Vn of V. Okay, so notice we're suppressing all the bases that each of these things depend on, but they are implicitly present. Okay, let's prove this. So, if you want to think of it another way, what this says is that you can split up M across products, matrix vector products like this. All right, cool. Let's see if we can do it. So, I won't write suppose all the way. I'll just do the SP. Suppose V is equal to B1 V1 plus dot 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 all the way down to Bn Vn for B1 through Bn some field elements. This is always possible since V1 through Vn. That list right there is a basis of V. So you can write every V as a linear combination of these basis elements. So there are some such scalars, okay, such that you can write V as a linear combination of those guys. Then TV, well, just use linearity. It's B1 T V1 plus all the way down to Bn T Vn. So I could have written T of V is equal to T of that whole thing, then split it up across addition, and then pulled out scalars, but I'll do it all at once since I think we're used to that at this point. Okay, cool. Hence, we have the following. These things are equal, so let's just take their matrices. Okay. The matrix of TV is equal to, well, we know that this M operation is linear. It's B1 M T V1 all the way down to Bn M T Vn. Okay, nothing too crazy so far, right? We just did the same thing to both sides and used linearity. Easy enough. But hey, the matrix of T of V1, well, we know that's equal to the matrix of T's first column. Oh. So the first column, dot comma 1. And then we can do this all the way down to the end. And then we get the matrix of T dot comma N. Oh, but wait a second. This just looks like the definition of matrix multiplication. That is, multiply a matrix by a vector, you just get out a linear combination of the columns of that matrix, and the coefficients are the entries of the vector. Oh, okay. Here, let me just write it out pretty explicitly. So, if I do MT dot comma 1, so the matrix of T's first column all the way down to the matrix of T's nth column, notice that this is just the matrix of T. I just wrote all of its columns like this. And then I write B1 on down through Bn. Then when I multiply, I just go across and I go down. And I multiply each thing and then sum it all up. That's what I get up here. But hey, that's just the matrix of T. And this over here, this B1 through Bn, these B's are the things that let me write TV as a linear combination of TV1 through TVN. MTMV. Or sorry, up here, V is this linear combination of V1 through Vn. The matrix of T is precisely this B1 through Bn, where V is B1, V1, plus all the way down to Bn, Vn. So here, V is B1, V1, plus all the way down to Bn, Vn. So this vector right here is just the matrix of V with respect to the basis V1 through Vn. Hey, matrix of TV is matrix of T, matrix of V. That's what we wanted to show. We are done. Cool. Let's keep it going. Okay, up next now, we're going to talk about the dimension of the range of a linear map and the column rank of its matrix. So if you remember, just in the last section, we talked a little bit about rank. We showed that row rank was equal to column rank, and then we just didn't really talk about it anymore after that. Let's bring it back into the picture. So here's the idea. If W and V are finite dimensional vector spaces and T is a linear map between them, then the dimension of its range is the column rank of the matrix of T. Equivalently, the row rank of its matrix, that is, its rank, this one quantity. Okay, here's the idea. So the column part there is what I'm saying. You can omit it because column rank equals row rank, and we just define the rank to be this number, whichever one you decided to take. Okay, so here's the idea of it. So suppose that V1 through Vn is a basis for V, and W1 through Wn is a basis for W. All right, so the map M, which is a linear map here, from W to F M, 1, that takes W and W to MW, which I'll write out as A1 through AM, where W is A1, W1 plus ... all the way down to AM, WM. This guy right here, this is an isomorphism. This is an isomorphism. Okay. Why? Well, think about the fact that W1 through Wm, that's a basis. So there is one and only one way to write each W as a linear combination of W1 through Wm. That is, these coefficients are unique. And since you could choose any coefficients you want and still get a W, this says that there are exactly as many W's as there are lists of coefficients A1 through Am. All right, cool. We already know this is linear. It's, after all, a way of taking a matrix tongue-tied. We already know this is linear. We've proved that before. So the fact that it is surjective and these two spaces have the same dimension is enough to show that it's an isomorphism. It's also injective by the fact that this is a basis, thus linearly, or that W1 through Wn, M is a basis, that's an M. The fact that it's a basis and therefore linearly independent means that the only thing that you can get out that's zero is when all the coefficients are zero. So this thing has a trivial null space, so it's injective. And since we're mapping a vector space of the same dimension, mapping between vector spaces of the same dimension in a linear fashion, injectivity is enough for surjectivity and to be an isomorphism. So either way, whichever you want to do, injectivity, surjectivity, both work. It's an isomorphism. Okay. Now, since the range of T is equal to the span of TV1 through TVN for T in LVW, i.e., here's the easiest way to think of it. Well, I won't even write the IE right there. Okay, so the range of t, that's all the things you get out from t. If you plug in a vector v to t, then you are taking t of a linear combination of v1 through vn. So by linearity, what you get out is a linear combination of tv1 through tvn. So everything in the range is a linear combination of the image of basis vectors of v. Okay, cool. So we know that they are the same. All right. That's a k. Take m restricted to range t. Okay. So take a linear map, restrict it to a subspace. It is still a linear map. This is still a linear map. I won't even say what it's in. So take this guy. Okay, this is an isomorphism from range t to the span of m tv1 through m tvn. Okay. But mtvk is equal to the matrix of t's kth column. So this says that range t is isomorphic to span of mt dot comma 1 all the way down to mt dot comma n, i.e. the range of t is the span of the columns of the matrix of t. So they have the same dimension, which is the rank of t. In particular, column rank, but column rank and row rank are equal, so we can just talk about the rank in general. That is, the rank is the dimension of the span of the columns, or the column rank at least. Row rank and column rank are equal, so we can just say rank, but to be clear, column rank is the dimension of the span of the columns of a matrix, and in this case, we're talking about the matrix of t. So when we say they have the same dimension, one of them is obviously the rank of the matrix of t. The rank of, I said t, I should say mt. Okay, there we go. Now we're done. What do you think? Not too bad? Maybe a little bad? There's kind of a lot of chasing things around here, but look through it again, think through it quick. Hopefully it doesn't seem too bad. All we did is we said, hey, look, I can send a vector w to I can send an element w in w, a vector in w, to a classic regular old vector where the entries are the coefficients in a linear combination of basis elements that let you write w as such a combination. Okay, now all you got to do is say, hey, the range of a linear map is the span of the images of basis vectors under that linear map. So we can take this m and restrict it to the range of t, which is a subspace of w. All right, so this says that range t is isomorphic to the span of the matrix of tv1 through tvn. But each of these guys, as we just showed a minute ago, i.e. over here, the matrix of t's kth column is equal to the matrix of the vector tvk. Oh, okay. So we can rewrite this span right here as this one down here. That is a span of columns. But the dimension of the span of columns is the rank. And we're done. Cool. All right. The next thing we're going to do is we're going to talk about change of basis. This is kind of fun. So notice, if you take a vector v and write it as a column like this with respect to a certain basis, then if you take a different basis, you'll get different field elements b1 through bn in this column vector. How can we describe what goes on when I switch from one basis to another? Here's the idea. So, the matrix product of linear maps. First off, let's suppose that T is a linear map from U to V, and S is a linear map from V to W. If you take U1 through UM to be a basis of U, V1 through Vn to be a basis of V, and W1 through WP to be a basis of W, then the matrix of ST with respect to the bases U1 through UM and W1 through WP. So ST, think about it real quick, T takes U to V, and S takes V to W, so this matrix ST, this product of maps ST, takes U to W. Hence we use the basis U and the basis for W. Okay. What we claim is that this is the product of the matrix of S with respect to the basis V1, Vn, and W1 through WP, and the matrix of T. That is, that you can break up the matrix here in this fashion. If you want to see this a slightly different way, this is a more explicit way of saying the following, which is that the matrix of ST is equal to the matrix of S times the matrix of T. This kind of quick way of writing it doesn't explicitly show what basis is being used in the middle. That is, you've only got U's and W's in this guy right here, but over here we have our V's. So those guys don't pop up over there, and if I just wrote it in this form, it wouldn't be clear what those V's were. If you just like it in this form, it's perfectly fine, it's still acceptable, but the whole idea is that this depends on a choice of basis for the intermediate space V. Okay, cool. So basically it says that you can break up the matrix over the product of linear maps over composition. Okay, here's the idea. So if we take the matrix of the identity operator with respect to two bases, we have a way of switching bases. So if U1 through UN and V1 through Vn are bases of V, then the matrix M of the identity with respect to the bases U and V there is the inverse of the matrix of the identity with respect to the bases V and U. Just switch their order. Both of these are invertible is the claim, and each is the inverse of the other. Okay, cool. So this idea here, these two facts will prove very, very useful to us. They come just straightforwardly from the definition of the matrix of a linear map. There's nothing fancy going on here, but this whole idea is very useful. So let's talk about it a little bit more. Let's prove a few things. So here's the first thing we get. It's the change of basis formula. The idea is as follows. So suppose you have a linear map from V to itself. Take two different bases, U1 through UN and V1 through Vn of V. Now, let's let A be the matrix of T with respect to the basis U. Okay, that is with this as the basis on one side and the other side. And let's let B be the matrix of T with respect to the basis V. Okay, and let's let C be the matrix of the identity with respect to the bases U1 through UN and V1 through Vn. Then A, the matrix of T, is equal to C inverse B, the matrix of T with respect to the other basis, times C. Okay, let's just try to write it out. So a lot of this is if it looks like it's not clear, it's just because we're kind of hiding things inside of notation. Here's the gist of it. So recall that we just said, we didn't do the proof of this, but it's just straightforward. It's just from definition chasing, that M, I'll write it ST of U1 through UN, W1 through WP. I'm not using the same U's and V's at the moment. I'm going to erase some of these to make it clear what's going on. But just to bring this back, okay, this is equal to the matrix of S. Oh, got an extra little thing up there. With respect to V1 through Vn, W1 through WP, and the matrix of T with respect to U1 through UM, V1 through Vn. Oof, long. Okay. Okay, so recall that this is true. Let me zoom out a tiny, tiny bit. For S in L, V, W, T in L, U, V, U1 through UM, a basis, UN, I guess, M, I should have M right there. Oops, UM. Basis for U, V1 through Vn, a basis for V, and W1 through WP, a basis for W. So recall the following. Okay, here, I'll even box this up just to make this clear that this is not the thing that we are directly doing. This is a result that we had just talked about a second ago right here, the matrix of the product of linear maps. Okay, so all we have to do is we just have to look at things here. This is almost a simple inspection type result. Okay, so since C inverse is just the matrix of the identity with the order switched here, this is V1 through Vn, U1 through UN, we have the following. So if you're all right with it, instead of writing U1 through UN and V1 through Vn and so on, here's what I'm going to do. I'm going to write them just as U and V, all right? If you want to be entirely clear, we should use V1 through Vn and U1 through UN and so on, but because it will get way too long if I do that, let's just not. Okay, so A is the matrix of T with respect to the basis U1 through UN. Okay. I'll write it as U. Okay. Cool. Okay. So here's the claim. Now what we want to say is that this is equal to C inverse BC. Okay, C inverse BC. Now all we have to do is basically plug and chug. In fact, let me make this slightly quicker. Let me write this as follows. Okay, C inverse BC, this is equal to, well, it's the matrix of the identity. And I'll write VU. Okay. Then the matrix B, which is the matrix of T with respect to the bases V. Okay. And then we got C, which is the matrix of the identity with respect to UV. Let me make that V look a little bit nicer. Okay, so the idea is just that you're switching the order for C inverse and C. All right, this is the basis with respect to v. We want to show that when you do this, you get the basis of t with respect to u. That is that we get out t u u. All right, so using this nice fact up here, so we got the v and the v match up, right? And so then we can turn it into, we can essentially collapse and remove that by putting the product here. Okay, so the v and the v match up, right? So this turns into the matrix of the identity times t. Now the v and the v match up. All right, so you get the u, which is the first thing on the t part over here, the second little bit. So I'll get a v from this one. And then I get the w, which is the second part of the first one over there, which is going to be the u, right? And then I have my matrix, the identity with my u and my v. Remember, these u's and v's are stand-ins for those whole long lists. Okay, so now I can do this again. I'll get the matrix of the identity times t times the identity. And now I just have to match up. Remember, we're matching up there and there. So first thing and last thing. All right. And then what I put in the second spot is the u, and what I put in the first spot is the u. Bam. But hey, the matrix of ITI, the identity t and the identity, that's just the matrix of t with respect to the basis u. Hey, that's A. So just to be clear, all the way through here, u is u1 through un. V is v1 through vn. So here, this is just shorthand. Okay, cool. So if you don't like that, write it out with them very long, and you can just directly plug and chug from this right here and our nice fact about the inverse of the identity with respect to some bases. But wouldn't you know it, we just got a formula to change the matrix of a linear map under different bases. So if you want to switch from one basis to another, you have to conjugate by C, where C is the matrix of the identity with respect to those bases. The basis you start with, V there in the second spot, and the basis you end with, U there in the first spot. Kind of nice. Okay, easy. Now this gives us something really cool. The matrix of an inverse is equal to the inverse of the matrix. So this is a consequence of the previous result. Let's think through it. Let's suppose that V1 through Vn is a basis of V, and T is an invertible linear map on V. Then the matrix of its inverse is the inverse matrix of T. That is the inverse in the world of matrices there. Okay, they're both matrices with respect to the same basis, but let's think about it really quick. So how can we get there? Well, we're going to use the previous result, and this one is kind of fun. So if you think about it, what can we do to get started? I might even leave this. I might only give you a sketch to start with, a hint. So maybe I'll end up spelling it out all the way. So what can we say about the matrix of T and its inverse? Well, the inverse of the matrix of T satisfies MT inverse is the identity. Yeah? Now, maybe we can do something fancy using different bases. Some bases for V in terms of the matrix of T and the matrix of its inverse. In particular, let's go back a little tiny bit and let's think about what we could do. In particular, do we know anything? Oh, I got to the right one. About, say, the column rank of an invertible matrix, something like that. Could you use something to that effect? There are a number of different approaches you could start with, but I claim that you'll want to write the matrix of T with respect to different bases, and then make use of the change of basis formula. From that, you should be able to use this little property right here, and then get out this nice fact. We'll leave it as an exercise for a moment. Maybe at the beginning of class next time, I'll give you a quick proof of it. How about that? But yeah, let's sign off for today. See you later. Have a good one.